Hello and welcome to this recorded e-learning on basic FPGA architecture for the Spartan-6 device family. My name is Frank Nelson. I'll be your instructor for this module. This module introduces slice and I/O resources available in Spartan-6 FPGAs. This basic FPGA architecture module limits its scope to discussing the slice and I/O functionality. Please note that there are also corresponding memory resources and clocking resources recorded e-learning modules available as well. After completing this module, you'll be able to describe the CLB and slice resources available in Spartan-6 FPGAs, describe the flip-flop functionality associated with the CLB resources, and anticipate building proper HDL code for Spartan-6 FPGAs. All Xilinx FPGAs contain essentially the same basic logic resources, slices, which are grouped into configurable logic blocks, commonly called CLBs. These contain combinatorial logic and register resources. As you can see from this picture, there are a lot of CLBs on this die. While each device family is offered with a different number of CLBs, determining which density is right for your application often requires you to at least synthesize your design before choosing an appropriate density of FPGA. Only with some experience can you properly estimate how many slice resources will be necessary for your design without at least synthesizing the design first. The slice resources are the most essential and fundamental to an FPGA design. They include LUTs and registers. LUTs are built to create your combinatorial logic resources, and each has an associated register with it. The LUTs and registers are grouped into slices, which also have other resources. Besides LUTs and registers, slices also have carry logic resources, which are designed to implement arithmetic logic functions with high-speed performance due to their dedicated carry chain, which runs vertically in columns from one slice to another. Spartan-6 is designed so that it only has one carry chain per CLB, and it is associated with the slices in column 0 of each CLB. The implementation tools select an appropriate routing that may include different kinds of routing resources. The solution that is routed is designed to try and meet your timing needs. To do this, it is important that you add timing constraints with the ISE design suite so you can communicate your timing objectives to the implementation tools. This will allow the software to choose the most intelligent routing solution to meet your needs. In fact, the mapping and placement of logic resources is handled by PAR, the Placement and Routing Utility. The Spartan-6 has routing besides carry chain logic. It is routed through the switch matrices. While understanding the interconnect structure is seldom needed, this diagram is meant to describe the population between slices and CLBs. You see, in between each CLB is a switch matrix, which is designed to connect to other switch matrices as well as neighboring CLBs. The possible interconnects are called PIPs, or Programmable Interconnect Points. Please note that proper use of global timing constraints, which is explained in the Essentials of FPGA Design course, is going to be required for you to obtain optimum speed. Now, combinatorial logic is stored in lookup tables or LUTs. Lookup tables are also sometimes called function generators. The capacity of a LUT is limited by the number of inputs, not by the complexity, so the delay through the LUT is constant regardless of what logic function is being performed inside. Each Spartan-6 slice contains a 6-input LUT that can also be broken into two 5-input LUTs. This allows the resource to be broken down if necessary to help assure maximum device utilization. Every customer must understand the input limiting nature of LUTs because many customers are used to building with ASICs. It is important to understand that the HDL code you write needs to be optimal for the FPGA. This is because ASICs are faster than FPGAs, and it's much easier to get good speed from an ASIC with suboptimal HDL coding styles. This is highlighted when you consider what you would get if your combinatorial logic had 7 inputs. Because the LUT has 6 inputs, your synthesis tool would be required to add a second LUT in series with the first. This would then dramatically increase the delay associated with this path and cut the maximum frequency possible. Also keep in mind that if you're trying to design at the maximum speed quoted in the device datasheet, you have to remember to limit all of your delay paths to one LUT or one logic level. This is not typical, but some customers do it by extensively using pipelining and by minimizing their combinatorial logic. The Designing for Performance course discusses pipelining. Every customer that builds his or her first FPGA inevitably struggles to get optimum speed because they're not using optimal HDL code. I recommend you listen to our HDL coding techniques RALs so you can be as successful as possible. Xilinx also provides the Xilinx Synthesis and Simulation Design Guide at support.xilinx.com for your reference. It includes terrific coding examples and detailed design recommendations. Each CLB contains 2 slices. From this diagram, you can see that each slice has 4 LUTs, 4 flip-flops, and 4 flip-flops that can also be programmed as latches. We added the additional registers because the LUTs can be broken into 5 input LUTs, and this should help designs get more out of an FPGA. The carry chain is also supported on 4 of the 8 flip-flops, and there are also dedicated muxes which can be used to build larger multiplexers and save LUTs for your system to get higher speed. In this diagram, we see a number of muxes used to connect the LUTs together. Each slice contains 2 F7 muxes that group the outputs of 2 LUTs and can create an 8-to-1 multiplexer. Each slice also contains 1 F8 mux that combines the outputs of the F7 muxes and can thus make a 16-to-1 mux. The mux outputs can drive out of the slice or connect to the available flip-flop latch if desired. These dedicated multiplexers are used to improve the speed of large multiplexers and save LUTs for other purposes. The reason that these multiplexers improve the speed of the design is because there is dedicated routing between the muxes that are low fan-out and fixed between the logic resources. It is also fast because the dedicated multiplexers are faster than building the equivalent logic just with lookup tables. What is most important to remember is that each of the dedicated resources has an intended purpose of saving LUTs and improving the speed of the design. And as an FYI, be sure if you're going to code for these muxes that you build them with a proper case statement. Carry logic is the dedicated hardware resource that improves the speed of arithmetic functions, such as adders, accumulators, subtractors, and comparators. From the diagram, you can see that the left-hand slices are grouped into one carry chain. Please note that carry logic propagates the carry signal vertically upward. This is important to note because most designs use carry logic extensively, and by using it, the least significant bit should be placed at the bottom of the carry chain. Likewise, when carry logic is used, bit ordering must be followed, with the less significant bit being placed beneath the most significant bits. Each slice has 4 flip-flop latches and 4 flip-flops. The difference between them, besides their programmability as a latch, is that the flip-flop latches, seen here labeled FF/L, can be driven by the LUT, carry chain, or the wide muxes. Conversely, the flip-flop can only be driven by an O5 input, which can come from the 6-input LUT when it is used as 2 5-input LUTs, or from a separate input to the slice. Now, these limitations are not much of a big deal. In the end, if you're building lots of lower input functions that share inputs, which is required if you're going to have the 6-input LUT broken into 2 5-input LUTs, you should end up with the flip-flops being used quite a bit. Otherwise, these extra flip-flops will probably be used for pipeline delay elements. All flip-flops and flip-flop latches share the same control signals. The group of associated control signals with a flip-flop is important since only flip-flops that share the same control signals can be grouped into the same slice. This means that if you don't manage the use of your control signals and try to reduce the number of control signals your design has, then you might have trouble getting high device utilization. The set and reset signal can be configured as synchronous or asynchronous. For synchronous design purposes, Xilinx recommends that unless absolutely necessary, you design with a synchronous set or a synchronous reset. Now, we discuss good synchronous design practices in the Essentials of FPGA Design course. To help designers with this, we have made a series of Vertex-6 and Spartan-6 HDL coding style RALs. They discuss the impact of this and provide you with many good design practices that will help you get high performance and high device utilization. So check those out. Many, but not all, LUTs in the FPGA can be configured as distributed RAM. This is a small 64-bit memory that can perform a single, dual, or quad port memory. Each port has independent address inputs and has a synchronous write and an asynchronous read. There are 4 configurations, as you can see from the slide. Most customers use these resources for DSP applications. Sometimes customers try to build larger memories out of these, but it is important to keep in mind that the extra logic used to connect them together will make the performance prohibitive. So only do it if you don't care about the speed of the memory. And in general, those customers that build with this are using the core generator or system generator to build a DSP application. Also keep in mind that if you're trying to build a larger memory, it might be better to actually target the block RAM resources that are dedicated to silicon, and that is usually easily instantiated from the core generator. Many LUTs can be configured as a 32-bit shift register as well. This is used primarily as a pipeline delay element for balancing pipeline applications, but it can also be used for variable length shift registers, synchronous FIFOs, CAMs, or for pattern generators. The SRL is also cascadable up to 128 bits in length. The most challenging thing with this is that most customers don't realize that it is not loadable, has no reset, and only offers serial in, serial out capability. So if you try to infer it with any of these behaviors, your synthesis tool will instead infer regular registers, and that could be a big waste. The benefit of this resource is that it can effectively provide the work of 32 registers with a single LUT. In pipelined applications, that is a huge savings. This is an example of the use of the shift register LUT functionality. The SRL can be used as a programmable delay element or NOOP. In this example, you see a 64-bit bus being processed through 3 operations, A, B, and C. A has a delay of 8 clock cycles, B has a delay of 12 clock cycles, and C has a delay of 3 clock cycles. Because the data processed is also grouped at its output with a multiplexer, these data paths must be synchronized so that the appropriate data is compared at the multiplexer. To do this, the shift register LUT can be used to delay the C operation by 17 clock cycles. Now, if we were to do this with registers, it would require 1088 registers. If we use the shift register LUT functionality instead, we only need 64 LUTs, each programmed for 17 clock cycles of delay. So this example uses 64 LUTs to replace 1088 flip-flops and the associated routing resources to complete this. Pretty good justification for using the shift register LUT. Because there are so many registers in FPGAs, pipelining is an effective way of designing to increase design performance. Because pipelines can sometimes become unbalanced when too much logic must be generated, it is necessary to delay some of the signals. And this is one of the best uses of the shift register LUT functionality, that is, to add balance to pipelined applications. So now that we know that each LUT has 3 different configurations, that is, logic, distributed RAM, and the shift register LUT, we can discuss the 3 types of slices in Spartan-6. So the slice M is a full slice functionality where the LUT can be used for logic and memory in the shift register LUT and has the wide multiplexers and carry logic associated with it. And this is 25% of the slices in your device. The slice L supports logic and arithmetic only. The LUT can only be used for logic, so not memory. It also has wide multiplexers and access to the carry chain, and this is used for about 25% of the resources in the FPGA. Finally, the slice X, which is a simpler slice configuration, supports logic only and is about half the device. The LUT can only be used for logic, not memory. There's no muxes and carry logic. Most customers don't use as many LUTs for distributed memory or the shift register LUT as you might think. So this segmentation of the functionality does not usually have a performance impact, but saves transistors for other purposes that will be more beneficial to the user. Also keep in mind that the implementation tools will lay your design out onto the die, so understanding which slices are an M, an L, or an X is not really pertinent to you. All we wanted to do was explain that they are different and show you how they are different. The input-output blocks, or IOBs, interface between the FPGA and the outside world. They are shown in this diagram on the periphery of the die. IOBs are grouped into IO banks located on each edge of the device. The IOBs contain registers and some specialized resources, but the main purpose of the IOBs is to clock data in and out of the FPGA. In fact, using the registers to clock data in and out of the device is the fastest way to move data in or out. Besides the registers, the IOBs contain interface logic that is designed to translate the internal voltage domain of the FPGA to whatever I/O stand you're using outside the FPGA. This saves you from having to add all the necessary interface logic outside of the FPGA. This requires that each bank share a common power supply for inputs, called a VREF, as well as the power supply for the outputs, or VCCO. These voltages vary by I/O standard, and the Spartan-6 supports many I/O standards. Fortunately, many of these standards can share the same power supply, so one of the things to keep in mind is we want to keep compatible I/O standards in those same banks, or group them into banks. Spartan-6 has 4 to 6 I/O banks, and this will depend on the device density, and each I/O bank has between 30 and 83 I/O pins, and of course that will vary by density and package options as well. The versatile Select I/O resource was first introduced with the Vertex family of FPGAs several years ago. It has been enhanced with every new product family ever since. I/O standards have been added and selected to support what our customers require. Spartan-6 FPGAs support over 40 I/O standards, including those you see listed here. But check the datasheet to see if your I/O standard is supported. That'll have the complete list. Note that there are memory-specific standards of various classes, differential standards that require 2 I/O pins to receive or transmit signals. The differential signaling standards include LVDS, LVPECL. The single-ended I/O standards include LVCMOS, SSTL, and HSTL. The Select I/O feature allows direct connection of the FPGA pin to external signals of varied voltages and thresholds. This optimizes the speed-noise trade-off and saves you from having to place interface components onto your board. All the dedicated interface logic already exists and can be selected on a pin-by-pin basis. However, note that to mix different I/O standards into the same I/O bank, you must be aware of the I/O banking rules. These rules apply because each I/O bank shares the power pins for each of the input and output pins in the bank. Specifically, the VREF powers the input circuitry and the VCCO pin powers the output circuitry. So whichever I/O standard you group into each I/O bank, make certain that the input pins have the same VREF and the output pins have the same VCCO. Now, this is easily planned with the pin-ahead utility that's included with the ISE design suite. This slide is just trying to show you how differential pins work in Xilinx FPGAs. Each pin in the device can be configured as single-ended, and most can be configured as differential. The differential transmitters are available only in the top and bottom I/O banks, specifically Bank 0 and Bank 2. The differential receiver and the receiver termination is available in all I/O banks. Note that these limitations have an impact on your pin layout, so be sure to plan on laying out your differential transmitter pins properly and early in the design flow. The primary use of the IOBs is for registering data. In this slide, you see that there are 6 registers associated with the IOB to support the use of double data rate applications. As you can see, there are 2 registers for input, 2 for output, and 2 for 3-state enable. However, the IOB can still be used for single data rate applications just as easily. Each register supports separate clocks and clock enables for input and output. The set and reset signals, however, must be shared amongst all the flip-flops. To clock the DDR registers, remember that you can use any pair of the PLL or DCM outputs that are 180 degrees out of phase, such as the clock 90 and clock 270 outputs, likewise the clock 2X and clock 2X phase shift by 180, or even finally the clock FX and the clock FX phase shift by 180. Besides the register and select I/O resources, there are also SerDes functionality built into each IOB. This includes both parallel to serial and serial to parallel conversion. This is a programmable functionality that can decode a wide range of signals. The O-SerDes I-SerDes combination is probably one of the most useful and radical developments. Many issues that you would traditionally address by using the FPGA fabric are handled within these blocks now. Tasks such as trading pattern recognition, clock-to-data alignment, and crossing of clock domains between high-speed serial I/O and slower parallel clock domains can now be accomplished with the dedicated logic included in the SerDes resources. When we couple these resources with the I/O clock resources, this feature becomes very significant and well suited for source synchronous applications. Now, we'll discuss the clocking resources and that corresponding REL. So we'll discuss that in another REL, and you can check that out. The I/O SerDes capability includes input and output SerDes resources. There is an O SerDes parallel to serial converter for both OQ and TQ. It is arranged as a master and a slave IOB pair to allow for differential inputs or larger single-ended bit widths. So not only can you complete, say, a 6-to-1 parallel and serial conversion, but when you pair these two pins appropriately, you can do larger parallel and serial conversion. For this to be done, an appropriate master serial pair must be found on the die. You can't just pair any two IOBs and make them a master-slave pair. So you'll need to either check the datasheet or use pin ahead to find out which of your pins are already pre-grouped. Now, let's take a short quiz to test your knowledge. Have fun, and we'll see you in a few minutes. Each flip-flop has 3 control ports: clock, clock enable, and a set reset port. You have to remember that the clock enable and the set reset port are active high. This is important when coding your HDL for the flip-flops. Likewise, note that there is not a separate set and reset port, just one port. And this port can be asynchronous or synchronous. This is important because your synthesis tool should be able to map the set or reset to a LUT input if it is designed synchronously. And as you'll see, this will give you some flexibility. This gives you more flexibility and is necessary for the tools to pack the most logic into the FPGA and get high speed, since all 8 flip-flops share the same control signal. So our recommendations are to design for active high control signals and build with synchronous sets and synchronous resets. Besides building synchronously, you should also try to use the FPGA's global reset functionality whenever possible. This will allow you to perform a global reset on your system using a dedicated routing resource. This requires the instantiation of your corresponding device's startup component from the Xilinx Unified Library and can save you routing a high fan-out signal to all of your FPGA resources. And don't forget to keep your control signals active high so you don't need a local inverter to be mapped to each control signal input. These are not dedicated in silicon, and that could force the synthesis tool to waste LUT inputs. The reason we have spent some time discussing the limitations of control signals is that they can limit your ability to get high device utilization and high speed out of your FPGA. The reason this is necessary is the implementation tools can only pack related logic together in the same slice, since there are a limited number of inputs to each slice. This is important with registers since all the flip-flops share the same control signals. Likewise, if the tools are going to use the 5-input LUT configuration, it has to be able to find another combinatorial function with 5 of the same inputs to be grouped into the same slice. You see, it's all about the grouping related logic into the same slice. If the tools can pack related logic together, that way it won't end up wasting LUTs and wasting registers, and you'll get the most out of the device. As I mentioned earlier, your synthesis tool can map clock enable and synchronous set or reset functionality to a LUT input. This is very powerful for being able to group registers into the same slice since all the flip-flops share the same control signals. In this example, we see how a clock enable and a synchronous set or reset is mapped to a LUT input. Now this is very helpful, but a job only your synthesis tool can do. But if you build with an asynchronous set or reset, then it can't happen. In that case, the asynchronous set or asynchronous reset would be forced to a register control port. Likewise, if you build with an active low control signal, the LUT will be required to invert that control signal by driving it to a LUT input. As I mentioned, flip-flops with different control sets cannot be packed into the same slice. So in this example, we see 3 flip-flops resynthesized to force some control signals to associated LUT inputs so that these registers can be packed into the same slice. Now this is accomplished by using XST's control set reduction option. Hopefully in the near future, all synthesis tools will incorporate this functionality automatically on every design. There are three ways to get the FPGA resources you need into your design. You can either infer logic with your synthesis tool, instantiate primitives from the Xilinx Unified Library, or instantiate an optimized component from the core generator. One of the biggest challenges for new users is to make certain that they are inferring the appropriate resources. First of all, one of the best ways to check that you're getting the best resources is to use your synthesis tool's schematic viewer. All of the high-end synthesis tools have schematic viewers. Viewers are used to graphically display a gate-level version of your netlist and also a technology view of your netlist. While a gate-level netlist is worthwhile to check the Boolean optimization produced by your synthesis tool, the technology viewer helps you understand what Xilinx primitives were inferred, or more importantly, what primitives were not inferred by your synthesis tool. A primitive is a resource that is written to the netlist that represents a particular FPGA resource, such as a LUT, shift register LUT, distributed RAM, etc. Xilinx provides a library of primitives called the Xilinx Unified Library to all of our synthesis partners, as well as to our customers, so they can create netlists that are optimal for their customers. While this same library is available to you anytime you want to instantiate a primitive into your FPGA. The core generator and the architecture wizard make larger optimized components available to you. While some cores have a charge associated with them, most do not have a charge associated with them. The cores range from simple components to large, highly complex IP. The architecture wizard, frankly, is most commonly used for creation of custom PLL and DCM components. All primary slice resources can be inferred by XST and Simplify. This includes LUTs, flip-flops, shift register LUTs, muxes, and carry logic. However, you must be sure to code for the resources properly. This means that if you define a flip-flop with an incompatible combination of control signals, you'll get something slightly different, probably with the LUT input used for a control signal. Likewise, the shift register LUT is non-loadable, has no reset, and only supports a serial functionality. So if you code for a parallel read, you'll get a pure register implementation, and this again may not be what you expected. Similarly, muxes need to be coded with a case statement, and carry logic should use the proper arithmetic operator. Don't code for the XOR functionality if you're targeting the carry logic, otherwise you just won't get it. In general, inference is best and preferred by our customers. It assures portability to another technology and is of course reusable. However, most customers will have to do some instantiation to get the most out of the FPGA. As I mentioned earlier, a list of Xilinx primitives and their behavior can be found from the Xilinx Unified Libraries Guide. This is available at support.xilinx.com or can be found from the Help menu in the ISE software. This will describe all the ports and attributes that can be customized. There is also a complete description of the XST attributes located from the software manual webpage. This is always a useful resource for inferring logic and learning good HDL coding styles. The core generator and architecture wizards help you instantiate a high-level component. These cores are optimized and make designing for all the detailed functionality of things like the DCM or the PLL a lot easier. They also provide access to some very powerful design tools that can create common, sophisticated components at no extra charge. In summary, all slices contain 4 6-input LUTs and 8 registers. The LUTs can perform any combinatorial function of up to 6 inputs or be implemented as 2 functions of 5 inputs. 4 of the 8 registers can be used as flip-flops or latches. The remaining 4 can only be used as flip-flops. Flip-flops have active high clock enable inputs and active high synchronous or asynchronous set-reset inputs. There are a couple of different slices as well. Slice cell slices also contain carry logic and the dedicated muxes. The mux F7 multiplexers combine LUT outputs to create 7 input functions or 8 input multiplexers. The mux F8 multiplexers combine the mux F7 outputs to create 8 input functions or 16 input multiplexers. The carry logic can be used to implement fast addition, subtraction, and comparison operations. The LUTs in the slice M can also be used as shift registers or 64-bit distributed memories. And finally, manage your control set usage so you can reduce the size and increase the speed of your design. Well, there's a lot of useful information about inference and synthesis attributes in the Synthesis and Simulation Design Guide. This is available from the ISE software using its help menu or directly from support.xilinx.com. The XST User Guide provides very helpful coding recommendations that all Xilinx users should live by. It also includes a detailed description about all of XST's synthesis options. This information can also be found from the help menu. If you would like to see what other courses we offer or what other free RELs are available, go to the Xilinx education link you see here. I would also like to mention again that there are architecture modules available that discuss the basics of Xilinx's newest devices. You may find this useful, especially if you want to learn more about the device differences. But whatever you do, please take a second and let us know what you thought of this REL. Just click on the icon on the next page and tell us what you think. Again, my name is Frank Nelson. You've been listening to the basic FPGA architecture module for the Spartan-6 device family. Thanks for listening, and thanks for your business.